We had already seen this familiar example where we had got 6 plots 1, 2, 3, 4, 5, 6 as identical as possible, and we had 3 varieties that we called 1, 2, 3. We picked up 2 of the plots at random, sowed variety 1, 2 remaining plots randomly, variety 2, and in the 2 remaining plots we sowed variety 3, continued for 1 season, then harvested and measured the yield. Now when we do this, the model that we used was this. So we had this yij equal to mu plus alpha I plus epsilon ij, I going from 1 to 3, I is for the variety, j is for the random error, and epsilon ij 0 sigma square, and all these are the parameters. So we have the coefficient parameters, there are 4 of them, mu, alpha 1, alpha 2, alpha 3. They are all real valued, they may take any value in R, and we have sigma square unknown. Everything is unknown, but sigma square is also positive. Now suppose we ask a very important question in such a setup, that is, are the varieties really different? So do they really differ in terms of their yield? That is typically the primary question that we shall ask. Now, if we want to ask this question, we are basically trying to make a test of hypothesis, where the null hypothesis is that they are not making any difference, and the alternative is yes, they are making some difference, that is, at least 2 varieties are different. Now, what is the null model? So under the null distribution, we are basically saying that we have shown effectively the same thing over all the things. So the varieties do not make any difference. So effectively, we have got only one variety, so to speak. So in that case, the model will be like this. We have got yij equal to mu plus epsilon I. I do not have that alpha I term at all. I have only mu plus epsilon I. Everything else is essentially the same, only the number of coefficients now is only mu and sigma square. So only 2 parameters to estimate, whereas here I had 5 parameters to estimate. Now be careful here. When excuse me, I am saying that this is a model, I am actually giving a family of distributions, where this mu, alpha 1, alpha 2, alpha 3 are actually the indexing parameters. So it's a set of all such things where mu, alpha 1, alpha 2, alpha 3 are in R and sigma square is positive. So these are the index parameters. So the index parameter here and the index parameter there, they do not have any relationship. So do not think that the mu here is same as the mu there. They are just index parameter. It is just like saying I can represent the entire R as all x cube when x is in R. The set of all x cube when x is in R. That denotes R. Similarly, I can write the set of all x to the power 5 as x is in R. That is also set of R. So I can say that these 2 sets are equal. But that does not mean that x cube is equal to x to the power 5. X is like the dummy variable. It is the indexing parameter. So though I am writing the same mu, the same epsilon, the same sigma square here as well as there, but this does not mean that they are the same things. So if over the same model I fit this and I fit that, the 2 mu hats that I will get will of course be different. The only thing that is common to both of them are the yij's. For the same yij's, I am claiming this model is a good fit and that model is a good fit. So the basic idea that we are going to discuss in this and some subsequent lectures is the idea of test of hypothesis in the context of linear models, and this is one example of that, where I have this full model and I have a restricted version of the same model. Observe that this is a restricted version. If you put all the alpha is equal to 0, then you get this. Or you might think of it like this: if I put all the alpha is equal to some constant number, then also I get a model like this, because the constant may be absorbed inside mu. So I can think of this, that this is a family, this is a set of distribution, that is another set of distribution. This set of distribution is a subset of that set of distribution. Such a situation is sometimes called restricted model, sometimes called nested model, and that's what we are going to specialize on.